Okay, here we are in our last lecture this semester about we finished with quantum mechanics and possibly a little bit of relativity later, a little bit. So what do you remember about quantum mechanics? You remember the wave-gravity duality? Everything is wave or particle, depending on the mass, the W wavelength, divided momentum large, short wavelength is more localized. We remember that the particles are represented by waves in general, or more precisely wave packets. A wave, normally depending on x and t. And of course, you will find in some problems, in some solutions, you will find some value here, exponential, plus another value, plus ta. These guys here are the eigenvalues of energy. So, I mean, there are cases where the system, in quantum mechanics, a system lives at the same time in different states. The famous Schrödinger cat, the cat is alive or dead, no? So it's both, alive and dead. And it can appear as alive if you measure in some specific times, and it can appear dead if you measure at different times. So that's the shocking part of quantum mechanics. For example, if you calculate the average value, some observable here, you will find that the quantity oscillates between two different points. Let's assume that you calculate, well, we will not see expectation values here, but it's good that you know that the expectation value in quantum mechanics of any observable average is this quantity divided by, which normally this is normalized to 1. The wave function is normalized to 1, etc. So my point is that in quantum mechanics, you cannot say that a system is sharply in a defined state. It can be in a superposition of different states. Then it's important to know that. Today we will solve a very easy system, very easy one. I think we solved the last time, the infinite potential barrier, right? I will delete this part for solving that system. Then imagine you have a particle here. This potential is infinity, and the particle is confined here between these two walls. This is only a one-dimensional problem. I will not put other dimensions. Then you can calculate the energy of the particle. The energy is related to some object we call Hamiltonian. Hamiltonian comes from classical mechanics. I didn't explain that part, but we use Hamiltonians in quantum mechanics. We use Lagrangians mostly in quantum field theory. And this has a reason. The reason those who want to study deeply these things in future is that the Hamiltonian is not a relativistic invariant. So it's applicable to systems where we are not in relativistic regimes. Relativistic regimes is velocities near to the speed of light. Okay? But in Lagrangians, the Lagrangian is a relativistic invariant. And this is the one we use in the accelerators for analyzing the dynamics. Naively speaking, the Hamiltonian is the kinetic energy plus the potential energy. Potential. It will rain strong. Can you listen? The Lagrangian naively is the kinetic energy minus the potential energy. This minus is important for the relativistic invariance I am talking about. And both objects, Lagrangian and Hamiltonian, they have the same information. They contain the same information, and you can transform from one to the other via a transformation called Legendre transformation. Legendre transformation, which has applications in many fields, in thermodynamics, in mechanics, and other fields, the Legendre transformation. And why is necessary this transformation? Because the Hamiltonian is a function of position and momentum, but this guy, Lagrangian, is some position and velocity. And it's not the same. Velocity and momentum are related, but they are not the same in the sense of variables. So this seems to be idiot, but of course we will not go deeply into this. This problem here I will formulate in terms of Hamiltonian because it's the easiest thing we can do. Remember that in quantum mechanics we don't use variables, we use operators. Then let's put it this way. The Hamiltonian of this particle will be the kinetic energy plus the potential energy. Since the particle is free to move between two walls, this potential is set to zero because it's free. There is only a barrier here and here, and this will operate as boundary conditions for the wave function, so I don't have to worry about that. So I consider only the kinetic term. In the sense of Hamiltonian, the kinetic term is momentum squared divided 2 times the mass. If I write in ordinary variables. But remember that the momentum, if we are working in the space representation, because remember the last class, if you check the video, many of you didn't come, actually, but you should check the video of the last class for understanding a little bit. In quantum mechanics, you have to decide whether you work in position space or momentum space. This has a reason, because when you are in position, for example, you locate a particle position, then you don't know its momentum. You have to sum over all the possible momentums. Vice versa, if you don't touch the particle, you can know its momentum because you know the temperature or whatever, but you don't know its position. So you decide one or the other, and this is uncertainty principle. The way to connect these two spaces is the Fourier transformation. Fourier transformation, which has applications in many fields, including quantum mechanics. Then, here, since we are talking about operators, this Hamiltonian itself will be an operator. Let's put it here. The Hamiltonian, I will put a hat like this. When I put a hat, it means operator. As an operator, it has to act over a wave function. And I will put that wave function in the position space representation, depending on space and time. No momentum and time. I could put momentum and time, and will be the same, but it's typical to use position and time. The last time I explained how the operators operate in different spaces is in the previous video. You can check it. So here, remember that the momentum applied over a wave function in position representation is minus EI h bar derivative. This is the way how the momentum operates over the wave function. It operates in this way as a derivative. Because this wave function is in the position representation. If it's not in the position representation, let's assume that it was in the momentum, it will be simply P. Like this. Like this. But instead, it's in the position representation, and that's what. I explained that the last class, how this is consistent with the uncertainty principle. Quantum mechanics, remember the uncertainty principle in quantum mechanics. We say position, momentum, equal I h bar. It emerged from this form of the form of this operator. Now, since this is P squared divided 2n acting over a wave function, then I have to operate twice. This operator has to act twice, 2 times. A square means operate with P and then operate again with the same P. Now let's do it slowly. Let's do it slowly. Let's put like this. I will put P to M, and I will operate with the first momentum operator like this. Right? Then let's do it like this. What is the form of this momentum operator in position representation? Is minus I h bar derivative. Then minus I h bar. Sorry, x. Then let's operate again. Let's operate again with P. It will be again minus I h bar. Minus and minus is plus. I squared is minus, so it will be minus h squared 2m second derivative. That's it. This is the way how the Hamiltonian operates over the wave function. It becomes like this. Then now this is a differential equation. This is a differential equation, and we can solve it easily. Okay? Any questions so far here? Until now? Questions, comments? You look confused, Egon. Explain, talk. Talk because we have time. I mean, we have the second part still. The Hamiltonian, we construct the Hamiltonian of the system. Kinetic terms plus potential. Kinetic, this is not different. This is the kinetic energy. Remember, classically, P is mass velocity, right? So at the end, this finish A1 mass velocity squared. But it's an operator, of course. This is an operator. It has to add over a wave function. That's the issue.
Under the operator squared, is it 2m or is it derivative of m?
No, 2m.
2m.
2m because it's the kinetic energy. If you replace this, let's put it classically. If you put mass velocity to momentum, m squared, v squared, m squared will cancel. The here is the traditional kinetic energy. But of course, in this case, it's an operator, and that's why we have to write in this way. Exactly. Okay. Egon is confused. See if I can find here something. Yeah, so it's clear, this part. You will find that the wave function here has to be 0 here. And it has to be 0 here. We need to know the length of this place, the length. And we can fix the reference. We can fix this x equals 0, and this is x equal L, or you could put x0 in the middle and put this minus L half or L half. It will not be any difference. There will not be any difference in this case. Yeah, I hope it's clear this part. Any questions so far?
That's a double derivative, right?
Yes, it's a double derivative.
Are we going to actually solve these equations in the exam, or do we just know, or do we only have to know the theory behind it?
Well, I will try to ask more like normal questions, but of course, this infinite barrier you should be able to solve. And this is an eigenvalue problem. Because anyway, the Hamiltonian apply the wave function is equal to the eigenvalues of the system times the psi. Okay, you should know this part. And then this is an eigenvalue equation which we intend to solve. This is what we intend to solve. Then this becomes a differential equation. Look at the face of Egon. It's then become minus h squared to m second derivative equal like this. Then at the end of the day, I can solve. I can just translate to let the derivative along here and translate minus e h squared below 2m psi here. This is a differential equation. I don't know if you in calculus you saw differential equations. You didn't see differential equations. You didn't see integrals, integrations.
Integration, yeah. No, we
But
didn't.
not differential equations properly. This is the weakness. I think the university has to work in these weaknesses because otherwise we will be defeated by other universities easily, especially in the job market. No? In the job market, when they demand, what do you know? No, I know how to dance. I mean, people say, yeah, what else? They will start to ask you. Okay. Then, when you solve a differential equation, you have to make an ANSAC solution, we call it. The typical ANSAC solution is you assume the wave function is a constant times an exponential lambda. In this case, to be like this, x, because we are considering derivative in x, right? This is the ANSAC solution. Right?
Could you show us, well, if we had to answer one of these questions, could you show us how we would go about the calculations?
So it goes what?
Could you like give us just an example?
Which calculation?
Well,
This is the example.
exactly, yeah. I mean, just how we would resolve
Yeah, this is
question in the exam. Like,
yeah. For example, I tell you, I put a particle between two infinite potential barriers. Find the wave function. I can ask you like that, and then you have to construct the Hamiltonian like this. You have to find this equation, and you have to solve. This is the ANSAC solution, and now you have to introduce it here. It's not over. It has not finished. Now we introduce this here. Then when you introduce that here, what happened? The second derivative of this is lambda squared, the constant exponential lambda. This is the second derivative. Remember, the derivative of an exponential is the same exponential times the internal derivative. I think you should have seen that in calculus, no? No? Okay. I will send you the sample solution in the next class or so. And actually, I think I have the sample solution of this problem done. I can project, I could have projected actually in this class instead of doing this from zero. Is okay, classes. Well, later I find that solution I can share with you. So the point is that you replace this ansatz here, you will obtain something like lambda square on the left-hand side is equal minus 2 em h squared. Lambda square, because this second derivative of this ansatz solution is lambda square a exponential, and on the right-hand side you replace a exponential. So in other words, here you put a exponential lambda x, which is the ansatz. But here in this part, you put lambda square a exponential lambda x. These two cancel because we want non-trivial solutions, and it remains this equation. This is the equation which remains here. Lambda square equal to this. And then lambda is equal to plus minus I root square 2em. Well, I could put h bar here. And already I have the solution. I found the wave function. Why? Because I have the two values of lambda, 1, 2, and I just replace here in this. So my wave function at the end is one constant. Let's put I h bar root square 2em plus another constant So this means that this solution oscillates between these two values. That's it. Easy. Any problem with that?
What you did with the ansatz solution, you derived it twice.
You introduce it here.
And you derive it twice.
Yeah, because you have to avoid the left-hand side of this equation. The left-hand side of this equation is second derivative of this equation.
So you derive it twice and you get
lambda square a. And then you put that here.
So lambda comes down.
And on the right-hand side, you replace the answer solution. It's a exponential. And then this cancel with this, and only lambda square remains. So you already have lambda square. That's it, easily. And now you already boundary conditions. When x is 0, the wave function is 0. Then let's put it, I forgot to put x here and x here. Okay. I must remark that there is an exponential of the energies here, which I don't write, because this is a stationary state. Well, I don't want to complicate you with that part. So anyway, when it's 0, it means that 0 is equal to exponential 0 is 1 plus b. So a is equal to minus b. That's what I said. So then I can group, let me write here. I can group this wave function. I can group like a exponential h bar minus this is why it's telling me the first boundary condition. The second boundary condition is telling me when x is equal to L, the wave function is 0 again. So 0 is equal to, since a is non-trivial, so I can just ignore it. There is x and x here, sorry. So it's telling me exponential L minus L. This has to be equal to 0. But this, trigonometrically, is 2i sine root square 2m E L h bar. and this has to be equal 0. So the only way how this is equal 0 is that the sign of this thing equals 0. And the only way how this is 0 is if this quantity here is multiple integer of n pi. So this quantity here will be equal to n pi. And this is how you get the conditions over the energy. N pi. When the sign is 0, pi, 2 pi, 3 pi, 4 pi, 6 pi, 7 pi, it will be 0. So there are many values which will give you 0. And this gives you the conditions over the energy. I will not solve this in detail right now because I will send you the solution. But this is the method. Let's do the method. Let's establish the method because I think this is your concern. Slowly now. What is the method?
But also,
Step 1. Okay. Also one. You have a question.
no, I just wanted to understand the transformation you did with the E into the sign.
Because this is a standard formula. Remember that sine of theta is A to I. This is a standard formula. We know it perfectly.
Oh, wait, isn't this a hyperbolic function?
No, the hyperbolic doesn't have the i's. If I delete this, if I delete the i's and I delete the sine, this is hyperbolic sine. Well, hyperbolics are exponential increasing or decreasing functions, but these are oscillatory functions. And finally, it's not over. Let's give you the conditions over the energy. It means that n pi is equal root square 2 MEL or h bar. Then give you the conditions over the energy, which is n squared p squared h bar squared 2mL. This is the energy of the system. This is the energy which this particle, the energy of the particle. And it has different levels. It's quantized. Because n can be 0, 1, 2, 3. It's quantized, the energy. And that condition comes from the boundary conditions imposed over this function. This is the trick. This is the beauty of the mathematics here. No? You can compare this thing, which seems to be, the comes out to be, to give you the energy levels of the particle. In mathematics, nothing is trivial. You have to elaborate it deeply. And then, after this, what remains? You have already the values of energy. You have this, the function is like this. You know the energy already, the energy levels. Let's put M here and N here. These are the energy levels are given here. What it means? I have to calculate the constant A. This constant A has to be calculated. And how do you calculate? Normalization condition. The sum of the probabilities is equal to 1. In quantum mechanics, is the same. But don't confuse the ordinary probability or statistics you saw in the school with the quantum mechanics statistics. It's not the same. Actually, it's not a statistic. Quantum mechanics, because we work with amplitude of probabilities. And in amplitude of probabilities, there might be interference between different terms. Let's say that there might be 2 eigenvalues that interfere with each other, like what happened in the wave patterns, no? The interference experiments and so on. But in ordinary probability, these interferences never appear. So what remains is to find the factor A, and that's found as follows. How do you find it? Well, this will be a bonus problem in the exam. Whoever made doesn't have to make many other problems which I put. How do you find that A? You have to integrate. You know that this has to be equal to 1. This is the product of two functions, or equivalent to the integration of the norm of the wave function squared This is one-dimensional problem along from minus infinity to infinity is equal to 1. The norm square of the wave function is telling you the probability of finding the particle in some specific region. This is the probabilistic approach of quantum mechanics. It's telling you the probability of finding, for example, you calculate this in the center, the probability will be higher and it will go to 0 at the extremes, at the extreme points. At the extreme points. And I must remark that the different energy levels define different functions. For example, for the level 0, of course, nothing happened. Or sometimes the wave function can behave like this. Or sometimes it behaves like this. Like this, for example. It can do these kind of things. And statistically, if you calculate, if we make experiments, it match. I mean, the experiments really are really saying that this is the behavior it should follow. Of course, this is the wave function, but the probability is always positive because it's the norm of the square of the norm, better. So this is always positive. How do you calculate this? Well, you take that function there, calculate a square, which is a squared integral minus infinity and infinity. This norm is in reality a product of psi function times the complex conjugate. So it means this complex conjugate means when you see I, you change the sign, plus and minus here. That's important in quantum mechanics. The complex conjugate, the adjoint operation is very important in quantum mechanics. And integrate over this, and this has to be 1. Then you solve a squared. A squared is 1 divided integration minus infinity and infinity of this product. Well, actually I did a mistake because this is not psi. Let's call this, I have to use a different letter. Tell me a letter. Let's put phi like this. Phi. Well, phi, what is phi? Phi is just the internal part without the A. So it will be exponential I squared 2me n, because there are different energy levels, h bar minus x and x. And
use the same, well, I mean, it would be more clutter, but if we just use the same symbol we used before, but we divided by a serve the same purpose.
well, as you wish, you can put everything immediately, but this a squared is what you want to solve.
Because the a's will cancel out anyway.
No, the a you have to find. This is what you have to find.
That a I will have to, but that's phi is the same as the.
Yeah, it's the same. This one.
But with the a, so
with the a,
and it will cancel out, and you calculate for the other a. That's outside the interval.
Yeah, exactly. We want to calculate this a. Then the conjugate is when you see I, you put minus. This is complex conjugate, and you replace the x in the integral, and you do the integration, and that's it, from minus infinity to infinity, and that's it, and you found a. Normally, I give you a number, 1 divided root square of 2, something, anything. So this is the way how normally we work in quantum mechanics. We have to solve the problem like this. But this is because it's a simple system. In more complicated systems, you cannot solve it so easily. And one example is the quantum harmonic oscillator, which is mathematically possible to do. I did by hand once in my life, but after you just go and see the results, and that's it, because you will not solve it every time you see it. It's too long for very solving. So I will explain the global methodology in quantum mechanics. Let me delete this. So more or less it's clear. I will send this problem solved. to you, and actually I already sent to you probably. I think I already sent this solution to you. So in quantum mechanics, the steps are as follows. First, the key point is first you formulate a Hamiltonian, which is kinetic plus potential operator. Then you transform that to eigenvalue problem. These are the stationary states, because in reality, these guys, this is derivative in time, the energy operator, derivative in time, the Hamiltonian. But at the end of the day, you will find that each contribution to the time will be an exponential minus I, the energy, and so on.
And the I is the imaginary numbers.
Yeah, imaginary number,
So
correct.
and that comes from you're doing the count when you're trying to determine the value of lambda, because it's minus 2 em divided by h bar squared, and when you square root it, you have to take out the I so that it's right.
I didn't get it, but can you
Because
repeat?
you have minus when you're calculating lambda.
Yeah. Because the root square of the minus, yeah.
Exactly.
Plus minus I.
Yeah.
And you have to introduce that. Yeah, you have to introduce that I. Actually, the I is important because if the I doesn't appear, it means exponential increasing or decreasing.
It's just because our professor for calculus talked about he glossed over it really because he was like, oh, but you guys, unless you're a scientist, which I mean,
of course you are a scientist.
Yeah, but he said unless you're doing sciences or engineering, you're not going to need imaginary numbers. So we didn't even do that.
No, actually, even in business and economy, they use imaginary numbers. That's because they want to make it easy. But to be honest, imaginary numbers, complex numbers is the most useful thing you will find in your life. One of the most useful things. But
our professor said, no, you guys aren't going to use it. And he just
even, for example, you can transform a problem which is in 2 dimensions. You can reflect in a complex plane, and you can make interesting analysis and operations. And it doesn't matter if it's economy, finance, business, whatever, you can do it. What happens is that, of course, the tendency is to be lazy, and people try, no, it's not useful. It's not.
Maybe we should remove this part from the video.
Yeah, actually, well, I think I cannot edit this thing. It's difficult to edit this thing. No, I mean, this is important because when people don't understand certain aspects of mathematics, they have the tendencies to underestimate it. I believe that it's not useful. It's useful. It's very useful. Super useful. Just a linear algebra in quantum mechanics, which of course we will not touch that part because it will be too much. But this part I didn't concern any time dependence. All what I did was to use this. Because we are assuming that all the states we are analyzing are stationary states. So that's why I didn't touch the time dependence. But the time dependence is also important, especially when there are different energy levels, and each energy level has a different time dependence. Then, of course, you will see that the system oscillates between 2 different states at different times, and there is a frequency of oscillation between different. Imagine the showing your cat, dead or alive. You have here the cat, dead or alive. Then there will be moments where there are times where the system is dead or alive, and then oscillate between these 2 states, come back, and so on. And whether you find this guy dead or alive depends on which moment you measure the system. And there will be moments where you measure and it will be partially dead and alive. It can happen also. It could be between also. But normally, well, this is an average. But when you measure, what you measure is the eigenvalues. So the eigenvalue, if the eigenvalue is dead or alive, then either you measure this or you measure the other, but with certain probability. better to say, well, I say, actually the statement I say just a few seconds ago is not completely correct. It's not, in the rigorous sense, it's wrong. What I should say is the following. At certain times, it's more probably to get alive than that. And at certain other times, it's more probably to get that than alive. But in between, for example, it could be 50-50% of getting that or alive. But once you measure, sharply will go to an agent value with the corresponding agent state. The agent values and the agent states, corresponding agent states, is what we measure in this experiment in quantum mechanics. Once you measure the system, the wave function collapses to one of the agent values, which you don't know what's that because you didn't see linear algebra or calculus 2. I like the previous system. Unfortunately, we eliminated calculus 2 in the. I think you, particularly scientists, you should see one more calculus. I mean, the business guys probably not, but I think the scientists should receive one more calculus because you need to understand what are agent values, agent vectors, and these things, which are very useful in this scenario. So anyway, you have this equation. It's a differential equation at the end. And you solve it. Solve, apply boundary conditions. This is the second one. Boundary conditions, and the fourth is normalize the wave function. This is the only problem I will ask to you. The only problem I will ask to you is the infinite potential barrier. What happens if this barrier is not infinite? The particle can penetrate still a little bit, up to some depth. And this is where some concepts come. For closing this part of the session, I will put this scenario without being rigorous, because at the end, I care is you to know some concepts. I will put this scenario. There is a particle moving towards some barrier. This barrier has some energy level, E. Then the particle will continue here and will find some inferior energy, E2, E1, and the particle, let's assume that it has an energy smaller than E1, but larger than E2. Let's assume this. Or let's put the opposite. Let's put, for simplifying, let's put the opposite. Let's put that this is E2 here, and this is E1 larger here. And this is a question which they always ask in conceptually to people. If the particle is moving here, at this point, it will feel some potential barrier opposing to you. I mean, with opposite, you are fighting against the potential. It's like finding a mountain. This is equivalent to a particle finding a mountain with some potential energy, but your energy is larger than the potential energy offered by the mountain. Let's put E2 here, because it's 2. Evidently, you will defeat this easily. You will cross by, but it will affect your motion. The fact that you have to defeat that energy, it affects you the way how you move. So obviously, the frequency, whatever change here, but still continue oscillating. Once the particle finds this barrier with energy superior to the energy the particle has, it's like finding a mountain here, a huge mountain with a potential barrier, and you are here with an energy which is inferior. Classically, you cannot climb this mountain, but quantum mechanically you can. then you can penetrate, but once you penetrate here, look at this curve here. You will start to decay here, the wave function decay. Part of the reason, you remember the eyes appearing the exponential? Well, in this region, these eyes will not exist, will be hyperbolic functions, decreasing in this case. The problem is solved exactly in the same way as we solved the infinite potential barrier, but taking into account these energies now, appearing as potential energies. No? Okay? And of course, boundary conditions and all this kind of thing. Then if the barrier is very deep, of course the wave function will decay to zero. But if it's not so deep, still the particle can penetrate and continue with some frequency of oscillation or so. Assuming that it has a single frequency, because it could be a bunch of wavelengths, no? It could be a wave packet. So the interesting part of quantum mechanics is that even if you don't have enough energy to defeat a potential barrier, you can do it with some probability. There is some probability to do that. But those problems are more complex, but exactly the same as we did now was calculating in each region, blah, blah, these kind of things. And we don't have time to go so in that. After the break, what I will complete is the quantum harmonic oscillator. I will just mention, I will just project the solutions, the algebra they use, the Hamiltonian, and I will explain the vacuum energy because it's so important. And then finally, we will talk a little bit about relativity naively, just for you to know about that. So I will stop this recording here.